Okay, in this video, we're going to cover section 5.3 from the Intermediate Algebra book, adding and subtracting radical expressions. It starts on page 189. All right, example 1 starts with the radical expressions square root of 7 plus 2 square root of 7 plus 9 square root of 7. All right, when you're adding and subtracting radical expressions, it's very similar to adding and subtracting combining like terms. You can only add terms that have the same radicand. So this has a square root of 7, this has a square root of 7, and this has a square root of 7. So we're going to add all three of those terms. If this was a square root of 5 or a square root of 6, you wouldn't be able to add it to any of these others. When you add them, you only have to add the coefficients in front. So this has the invisible 1, and this has a 2, this has a 9. They all have a square root of 7, so I'm going to add all three of them together. 1 plus 2 plus 9, that's 12. So the coefficient is going to be 12, and the radical stays the same. Letter B is 1/2 the square root of b plus 3/4 the square root of b plus 3/5 the square root of d. And again, you can only add them if they all have the same radical, which they do. They all have the square root of b. To add them, we're just going to add the coefficients in front. So this is going to be one of your favorite things to do, fractions, and I know that. So we're going to have to add these fractions to get a new coefficient. We're going to add 1/2 plus 3/4 plus 3/5, and that's just these coefficients here in the front. To add these, they all have to have the same denominator. So the common denominator for 2 and 4 and 5 is 20. So we're going to change these all to a denominator of 20. To get a new numerator, you multiply. 2 times 10 makes 20, so 1 times 10 gives me 10 on the top. 4 times 5 makes 20, so 3 times 5 gives me 15 on the top. 5 times 4 makes 20, so 3 times 4 makes 12. And when I add all those together, the denominator is going to stay 20. I'm going to add 10 plus 15 is 25, plus 12 is 37. So that will be the coefficient. And the radical will still be the square root of d. Because that's what I have here, square root of d, square root of d, square root of d. So just add the coefficients together, get a new coefficient, the radical stays the same. All right, for letter C, I have 4 times the cubed root of 11x plus 3 times the cubed root of 11x plus 24 times the cubed root of 11x. Again, you can only add them if they have the same radical. And since these are all cubed roots of 11x, we're going to add them by just adding the coefficients in front. All right, 4 plus 3 is 7. 7 plus 24 is 31. So this becomes 31 times the cubed root of 11x. Letter D says the fifth root of 3y plus 3 times the fifth root of 3y plus 12 times the fifth root of 3y. Can I add these together? Yes, I can. They all have the fifth root of 3y. And do not forget the coefficient here is 1, not 0. So this is 1 plus 3 plus 12 is 16. So this is going to be 16 times the fifth root of 3y. All right, example 2 is on page 189. Letter A says the square root of 12 plus the square root of 27 plus the square root of 48. And like we talked about in the last example, you can only add these if the radicals are the same, which they are not right now. But these can all be simplified. So we're going to simplify them before we try to add them. If you remember simplifying, or previous section, you're looking for a perfect square factor of 12. What's a factor of 12 that is a perfect square? And that would be 4. So this is basically 4 times 3, which makes 12. The 4 is a perfect square, so we can square root it. When we square root 4, we get 2, so there's going to be a 2 here. So this would be 2. The 3 has to stay underneath. So the square root of 12 turns into 2 square root of 3. We're going to do the same thing with the 27. The perfect square is 9. So this turns into, when we bring the 9 out, 3 square root of 3. And 48 is 16 times 3. The square root of 16, when it comes out, is 4. So this is 4 square root of 3. Now I can add these because they all have the square root of 3. I add the coefficients. 2 plus 3 is 5. 5 plus 4 is 9. So I end up with 9 square root of 3. Letter B says square root of 50 x to the 7 plus x square root of 32 x to the 5. If you remember, you can only add these if they're the same, these radicands, and they are not, so we're going to have to simplify first to see if we can make them the same like we did above. Alright, so 50 is 25 times 2. And x to the 7, when we break it up, we can make it x to the 6 times x, because you always want to make your exponents into an even and one extra. When we square root this, this is going to be a 5 coming to the outside, and the square root of x to the 6 is x cubed, so we're going to have a 5, and we're going to have an x cubed on the outside. So this is going to be 5x cubed square root of 2x, because that's what's left in. So this coming to be the 5. When you square root an exponent, you half it, so this becomes x cubed. This 2 is left underneath, and this lonely x is left underneath. Over here in the second term, we have this x coming from here on the outside, and then we're going to break this 32 up to see what we've got on the inside. 32 is 16 times 2, and the x to the 5th is x to the 4th times x. This 16 becomes a 4 when we bring it out. Square root of 16 is 4, and this x to the 4th becomes an x squared. So on the outside, still have this x that we're starting with. Then we have a 4. Then we have an x squared. Left on the inside, we have a 2x. We're going to simplify that here in a minute. So this x, still here. Square root of 16 is 4. Square root of x to the 4th is x squared. This 2 left under, this x left under. Now, we need to simplify all this. When you multiply these, remember there's an exponent of 1 here. So this is going to be 4x cubed, because there's an x to the 1 and an x squared. So this is really 4x cubed square root of 2x. Now, can we add it to this term up here? Yes, we can, because they both have square root of 2x. So 5x cubed plus 4x cubed makes 9x cubed, and the square root of 2x is still there. Letter C says the cubed root of 8p to the fourth plus the cubed root of 125p. And we're going to simplify these so that we can see whether we can add them or not. 8 is a perfect cube. 2 times 2 times 2 makes 8. So the cubed root of 8 is going to be a 2 on the outside. So we'll bring that 2 out. When you find the cubed root of an exponent, now we're not dividing by 2, we're dividing by 3. So 3, how many groups of 3 can you make? You can make 1. So that's going to bring a p to the 1 power on the outside, but it also leaves 1 left on the inside. So take your exponent, divide by 3, that goes 1 time with a remainder of 1. So this simplifies to make this. The cubed root of 125, which is a perfect cube, is 5. 5 times 5 times 5 makes 125. So this is going to have a 5 on the outside. But I can't make any groups out of this p because there's only one of them, and I need 3 to make a full group. So this 1 is going to have to stay in by itself. So that means I can add these because they're both square root of p, but the coefficients are not like terms. I can't add 2p plus 5. So I'm done, basically. This is all I can do. We could rewrite this, and some teachers do like to have this rewritten as the coefficient in parentheses on the outside with the radical next to it. So this is what would happen if I could add these coefficients. They would be added on the outside with the square root of p like this. Personally, I would accept either answer, but some teachers prefer this answer, so you probably need to check with your teacher. Okay, letter D is on the next page, so turn the page. Letter D says square root of 50 plus square root of 15, and we need to simplify these before we can add them. So there's a 25 times 2 in the 50. 25 comes to the outside as a 5, so we get 5 square root of 2. The 15 does not have any perfect squares in it. The only factors of 15 are 5 times 3, and neither one of those are perfect squares, so there's nothing that we can bring to the outside like we did this. So this is not going to simplify. It's just going to stay as the square root of 15. So now, when I look at these, I can't add these because they are not like radicals. So this is the final answer for letter D. Letter E says the fourth root of 32 plus the fourth root of 162 plus the fourth root of 2 over 81. All right, and this can be a little bit tricky, but when you're dealing with higher order roots, fourth roots are not too bad because you can break these down into prime numbers if you want using the tree, or you might know fourth roots because it's really not too bad. We know 32 is 16 times 2, and 16 happens to be a perfect fourth because you can take the square root of it twice, or 2 times 2 times 2 times 2 makes 16. So when you break this to be a 16, the fourth root of 16 is 2, so a 2 is going to come to the outside here. So we're going to end up with 2 times the fourth root of 2 when we simplify that first term. The second term, on the other hand, you might want to use prime numbers. See if you can look for 4 of the same. If you break this down using prime numbers, you end up with 3 times 3 times 3 times 3 times 2, using the tree and all that. And I'm not going to show that because you should already know that. But that basically tells you that there is a group of 4 3s here. When they come to the outside, they'll be this one. So this is going to be 3 times the fourth root of 2. And already I can see this is pretty good here because they both have a fourth root of 2. I'm going to be able to add those two terms together. Now, with this fraction, I don't know if you guys recognize the 81 was these 3's right here. So 81 is a perfect fourth, okay, and also 1 is a perfect fourth. So to simplify this fraction, you might want to just break it up to be 1 over 81 times 2. Or in other words, bring that denominator down. And now this is a perfect 4, because the fourth root of 81 is 3. That's where these 3's come from over here. So the fourth root of 1 over 81 is 1/3. And then this 2 can stay underneath, like this one did. So we have 1/3 times the fourth root of 2. And now you can add these because they're all fourth roots of 2. You're going to add 2 plus 3, which is 5, plus 1/3. So 5 and 1/3 basically. But we don't like mixed numbers, so we're going to change it to an improper fraction. 3 times 5 is 15, plus 1 is 16. So this equals 16 over 3 times, bring the radical back, the fourth root of 2. All right, so working in example 2, we're going to do letter F, which says the fifth root of 32 plus the fifth root of 96. All right, and we might need to use some prime factors here. I happen to know the prime factors of 32 are actually 5 2's. So what you have here is your group of 5 2's. Comes to the outside, it actually makes just 2. So this is 2. There's nothing left underneath because you used all these 2's to take the fifth root. So this first term simplifies to just make 2. The second term, on the other hand, I don't know. There's a 32 in there, 32 times 3. So we could say this is 32 times 3, since we know 32 is a perfect fifth root, don't we? So the fifth root of 32 is 2, just like we did over here, and the 3 will be left underneath. So this is going to be 2 times the fifth root of 3. And you can't add these together because they don't have the same radical. So this is finished. This is your simplified answer here. Okay, we're going to do example 3 now, which is on page 190. Subtracting. So letter A says 5 times the square root of KP minus 7 times the square root of KP. The rules for subtraction are exactly the same as addition. You have to have the same radicand, and then you just add algebraically using signed numbers. You add the coefficients. So basically this is 5 plus negative 7, or 5 minus 7, which comes out to be negative 2. But before I do that, I probably should write the third term on, because I missed the third term. So negative or minus 4 square root of KP. I almost missed that one. So now, 5 minus 7, negative 2, plus negative 4 makes negative 6. And the square root stays the same. So it's just like addition. It's just using signed numbers with the subtraction. Letter B says the fourth root of 3 minus 5 times the fourth root of 3. Again, can we add these slash subtract? Yes, we can, because they have the same radical. This is a 1. Don't forget the 1. So this is 1 minus 5 makes negative 4. So we have negative 4 and the radical, the fourth root of 3. Letter C. Says Negative 2 times the cubed root of 5 minus 9 times the cubed root of 5 minus 13 times the cubed root of 5. Can we add these? Yes, we can. They all have the cubed root of 5. So negative 2 minus 9 is negative 11, minus 13 is negative 24. So our coefficient is negative 24. Our radical stays the same, cubed root of 5. Letter D says negative sixth root of x minus 5 times the sixth root of x. So don't let this confuse you. This is still a coefficient of negative 1. And this is a coefficient of negative 5. Can we add them? They're both the sixth root of x. So yes, we add the coefficients. Negative 1 plus negative 5. And I missed getting that third term on there again. So it says minus 3 sixth root of x. They all have the same radical. So negative 1, negative 5 makes negative 6, plus negative 3 makes negative 9. So negative 9 times the sixth root of x. Okay, for example 4, which is on page 190, we're still subtracting radical expressions. Letter A says the square root of k cubed minus 9 square root of k cubed minus 2 square root of k cubed. All right, we can add these. They all have the square root of k cubed. We add the coefficients. 1 minus 9 minus 2. Well, these two negatives together make negative 11 plus 1 makes negative 10. So we end up with negative 10 square root of k cubed, which is a great answer, except it's not simplified because there's a perfect square in here. K cubed can be separated out to be k squared times k, which is a perfect square here. So this will come out to the outside as an extra k. The negative 10 will still be there. So we'll end up with negative 10k square root of k. Just to recap, this negative 10 is still here. This k cubed got separated to be k squared. Remember, when you're trying to find the square root of an exponent, if it's more than 1, there's a perfect square in there. Make it an even number and 1 extra. Divide it in half to bring it to the outside. So that's where that k is coming from. The square root of k squared is k, and this one has to stay in because it doesn't have another one to go with it. Letter B says the fourth root of 32 minus the fourth root of 162. And if I'm not mistaken, we did both of these. We simplified back in example 2. So you can refer back to example 2 if you are confused about those two terms. But we have another term here, minus the fourth root of 2 over 81. All of these three terms we simplified back in example 2. So if you want to scroll back there to see, this one turns into 16 times 2. 16 is a perfect 4. So the fourth root of 16 is going to come out as 2. So this is 2 times the fourth root of 2. This 162, remember, was 3 times 3 times 3 times 3 times 2. So you have this perfect 4 in here. So this is going to bring a 3 to the outside. So this is going to be 3 times the fourth root of 2. So that 2 right there has to stay in. And then this one, remember we made this into 1 over 81 because 81 is a perfect 4. So we're going to make this into 1 over 81 times 2, which is equal to 2 over 81. So take your fraction, there's a perfect fourth root on the bottom, 1 over 81 times 2, and this, the fourth root of 1 over 81 is 1/3. So we're going to make this into 1/3 times the fourth root of 2. So if I'm not mistaken, these are the same exact terms we had in example 2, letter E. Now we're just subtracting them instead of adding them. So to subtract, we're going to take these coefficients. This one's positive, though, and these two are negative. So let's give them all the same denominator of 3, and that might make it easier for us. And I'm going to ignore the radicals for right now. I'm just going to deal with the coefficients. Give these all a denominator of 3. That would be 6 over 3 makes 2, 9 over 3 makes 3. So this turns into this turns into this. When I add these together, these two are negative, so this makes negative 10/3. But this one's positive, so this is positive 6 plus negative 10 makes negative 4. So the coefficient here is negative 4 over 3. And the radical is the fourth root of 2. So just bringing this radical back. So 2 turns into 6/3, 3 turns into 9/3. We did that because this one had a denominator of 3, so we wanted to make these two match. This is a positive, these are both negatives, so when you add them, you get negative 4 over 3. And that's your answer there. Alright, letter C. Letter C. The square root of 72 minus the square root of 13. Now 72 will simplify. So 72 is 36 times 2. 36 is a perfect square, so when it comes to the outside it'll be 6, and this will be 6 times the square root of 2. However, 13 has no factors in it that are perfect squares, so it cannot simplify. So it's just going to stay as a square root of 13. And when I look at these, I see I cannot add these because they are not like terms. So this is a final simplified answer for letter C.